Okay, the angular momentum principle. So we've looked at two things. We looked at torque, and so I'll write down all the definitions of torque. Torque is equal to R cross F. That's the best definition. Torque is a vector, but if you want to deal with it in one direction, torque about some point O is equal to R, which is the distance from the point of rotation or the point of interest. It doesn't really matter. This is R. And if I push with some force F, that's F. So it's R, the magnitude of R, the magnitude of F, times the sine of the angle between R and F, which is the same as the cross product. I could also write this as equal to R perpendicular F or R F perpendicular. So if I push with a force like this, I could use this distance or I could use this force. Okay, so that's my definition of torque. And then we also had the definition of angular momentum. L equals R cross P, where P is mv, and again R is a point of interest. But if you force it into one direction, we can write this as R P sine theta. And this is for a point mass. If it's a large mass, we can write this as I. It's actually still a vector. Omega. This is about a fixed axis, where I is the moment of inertia and this is for a rigid object, sum over I, mi, ri squared. Now what about the connection between these two things? This is where we get the angular momentum principle. This says that the net torque about some point O is the change in angular momentum with respect to time. So this may look familiar. It looks like the momentum principle. F net is the change in momentum with respect to time. And just like this, we could say this is m delta v over delta t equals ma. And in a lot of cases, we can do the same thing here. I could say this is I delta omega delta t, and we may not want to write this as a vector, but the change in angular velocity with respect to time is the angular acceleration, so I get I alpha. Let's write this as scalar. And so that's another way of writing it. So in short, momentum is changed by a net force, angular momentum is changed by a net torque. And like I said before, I actually could represent this as a whole bunch of individual masses and still use the momentum principle. But once I get rigid objects, large objects, it becomes too complicated to do that. So we deal with this angular momentum term. And in fact, here's a secret. In quantum mechanics, we have angular momentum that seems to be very similar to this, but it's kind of like an intrinsic angular momentum. It may not actually be angular momentum, but we call it that, and it works just like that. So, and you couldn't break it into points. Okay, that's your introduction to the angular momentum principle.